much. We have a visitor from the Technical University in Munich, Jovana. Pronounce your last name for us.
Knežević.
All right. And everyone's been working on pronouncing her last name.
Please, after presentation, just come to me and...
She is, will be spending 3 months, the next 3 months, here at the Ski Institute and working with us. She works in computational science, specifically looking at integrating these problem-solving environments and doing interactive steering. So integrating visualization with computing, and we have some interest in doing that as well. And I thought it would be great if she could give a talk so everybody knew what she was working on, and then she could, you guys could follow up with her and vice versa. So let's give us an overview of your work.
Thank you very much for your introduction. So thanks to Professor Johnson who invited me, and also Magali and Deb who helped me organize my stay here. You will be seeing me around until the end of January. So today I will talk about interactive computing, which is the main direction of my research, but not before I have this chance to thank all of you for this opportunity to explore and experience all the great things that you're doing. And as you can see, I have captured my first try with the ski run, so it was more or less successful. You can judge. What I found also very nice was opportunity to eat donuts with you, which I also realized should not be put into the toaster. And of course, it's a great pleasure to be at this lunch and today to present our work. So what interactive computing is all about? It's in general any kind of user interaction with the program during the program runtime in order to estimate its current state or its tendency and hopefully be able to react on this. So of course when you define it like this, you may think also on playing video web games, but in our research we concentrate on engineering applications. And here a typical scenario is that you have an engineer with his sophisticated graphical user interface, and he tries to interact with the running simulation. So it may either run on his own computer or somewhere on a cluster that he can access remotely. So what happens here is that the data about the change, if he tries to modify something, is sent, for example, over the network to the simulation, and then the obvious challenge is how to let know the running simulation, which is sometimes also a time-consuming one, that something has happened, that it should apply these changes and recompute it with new settings, so that the results, the new results can be seen by the user immediately. And this is where our framework comes into play with hopefully only few code changes on the simulation side and relatively simple coupling of these two components, so the graphical user interface and the simulation at the back end, provide real-time feedback to the user. And when I say feedback, you will see later what I mean. So first of all, if this girl maybe reminded you on Alice in Wonderland a little bit, don't be surprised, it is her, really, because my whole motivation story was kind of growing up, or realizing that things are not as they seem at the first sight. So I have to tell a short story. When I came first to the chair where I'm currently doing PhD, they already had some interactive applications, and which was really nice to see. They had, I remember, even some collaborative environment where they could simulate the heat ventilation, the ventilation system, so they were simulating the airflow in the room, and even several clients could connect and together move the people around the room and see how the flow changes. So it was really cool, and I said, yeah, I would like to work on something like this. But then when I started, they gave me just a 2D simulation example. So you can see I got this graphical user interface, which to visualization guys it may look a bit funny, but what they told me, there's a 2D simulation of heat conduction, and actually what user can do is specify a boundary there, and then of course a grid, generate a grid, and then one can insert the heat points and then move them interactively and watching how the temperature distribution changes. So what you have basically is update of the temperature according to the temperature in the neighbor cells, and this is done iteratively. And 100 times 100 grid, it was all very fast and nice, so completely interactive. And then my supervisor said, yeah, now generate 300 times 300, and you will see right now what happened. So first we specify the boundary, as I said, and then I try to insert a heat source. And then we were waiting. So actually this is the problem. There is a very fixed order how the things are executed. So you have interaction, then you have simulation, applies the change, calculates everything, and only then you get the results. So you see. And in the meantime, you're not able to modify anything. So then they told me that I should work on this. Yeah, well, of course, this does not mean that all these applications are not nice. They're nice, but maybe it was not the main focus of the developers to work on the steering. Now I have to cite the article we all got some days ago. So it's my research problem, so I have to tackle it. I have no choice. And all of this because we want to make the application area wider. So all the steering concepts that we usually see in other interactive environments are such that they're not applicable to wide area, so to wide area of engineering applications. And what we want, and what I'm sure you all want, is really to investigate even long-running and resource-intensive applications during runtime, which is, of course, at the moment just a dream. And for this, there are things that one has to consider. And they all sound very, very trivial, but are usually not taken into consideration, are not taken seriously. And first of all, you have to be able to let know about the update. So you have to send this update immediately. You saw before when I tried to insert the heat source, it did not even recognize that I'm doing something on my user interface. And then the simulation, which is running in the background, let's say, has to see that this happened. So it has to be interrupted somehow, and the results have to be received instantly, so that you can then, in timely fashion, as you like, visualize the results in some intervals. Of course, for this one has to transfer the simulation results very quickly, which we haven't tackled so far for very large data sets. So this is also something to think about. And now I'm going to talk about how what is our approach to interrupting the running simulation. So what is a typical approach is that people insert checkpoints in the code, which really violates sometimes the code, and it's also very inconvenient because sometimes you simply do not know where to insert these checkpoints. It's very simulation specific, and if you have iterative solver, you may say, yeah, we inserted at the end of one iteration, but on the other hand, it may one iteration may last too short or too long, or so it's not so good approach, I would say. On the other hand, one can assign just one thread to wait for the user interaction, which is also a waste of resources. And our idea is to shift this control from the code actually to the operating system somehow, in a way that we invoke signals every small at the expiration of every small interval. For example, you set kind of alarm to ring each millisecond and do the check for updates. And then we make sure that if something happened, the rest of the old computation is skipped and the computation starts over again with the new settings. This all sounds nice. On the other hand, it gets much more complex when you have multi-threaded application. Some of you know it's not very nice to work with signals and threads together, so there are many things to make sure of before you decide to use this. Oops. So you have to ensure memory consistency and data consistency and stuff. So far we're gaining experience. We do not have any problems with the applications that we integrated the framework on. Nevertheless, I would be interested to try the concept on as many applications as possible, because each of them has some specific things which then we can realize maybe we would have a problem with something, something new, some new issue. And with distributed parallel simulations, we also try this concept. And what is surprise, but the kind of good news, is that the overhead which is caused by the framework itself, I mean, you can imagine this alarm ringing every millisecond. It did not, so far we did not notice that it caused a significant overhead of, when we compared the execution time. So nevertheless, the synchronization issue was also we had good results for up to 100 processes. So there were no synchronization latencies observed. But to be honest, I mean, I'm not here just to present look how great this is. I really need some feedback from you, and I do not know what would happen if you would try this on massively parallel simulation. So if one would have 100,000 processes, for example, and each of them having his own alarm ringing, then I really do not know what would the performance look like. In our example, we were using hierarchical broadcast. So that we do not have a bottleneck at one master process trying to inform all the others. But as I said, we have just tested it for maybe 100 processes. And now going back to our example of heat conduction, let's see how we were solving the problem that you just saw on the video. So first of all, we were interrupting the simulation. As I said, it was iterative solver, and in the signal handler, we were manipulating indexes in the nested loop, so that the simulation recognizes if something happened, for example, and the indexes are set in such way that when you go back to the code, you're out of the loop immediately, So then you skip the rest of the computation and start with the new settings. And this was nice, but one could not see the equilibrium reached when one would move the heat sources all around the screen. It's too frequent, and the simulation does not finish. So you can see several iterations, but you do not see the how the temperature distributes on the whole domain. And this is why we were playing with several hierarchies, so with doing the computations on several grids of different resolution. So the coarsest one was 75 times 75, and the initial grid, as I said, was 300 times 300. So when one would start to move the heat sources or boundaries around, it would switch immediately to the coarsest grid. Then the user gets immediately the feedback, and then when he's satisfied about the current setting, he stops interacting, then he gets the results on the intermediate and on the coarser grid. So depending on the frequency of user interaction, we had switching to all these different grids. And this hierarchy approach is not exactly the part of the framework. I mean, this is something which is very also simulation specific, and you will see the other hierarchy that we were using on other applications, but it is the general idea, something which we try to apply. And then, not to waste the results we gain on the coarse grid, we were using the results on the coarser grid as initial guess for the finer grid. Although, I mean, I do not know, it might introduce small error, but it's temperature, so it's smooth, and we believe it's for this purpose it's fine. And now I'm going to show you exactly how it looks like. So this was without using it as an initial guess. So you see, for example, we insert the heat sources, and now we move it. We have one grid, then second grid, and finally the third one. So this is the way it was working. But you see here, of course, we were using zero vector as initial guess. So this is why I will show you right now the other example. So now the visualization is a bit different. You can see the grids here better, I believe. This is why I switched to this kind of visualization. So this is second grid, and now the finest one. So I mean, it is just 2D simulation, but still I think it demonstrates the concept well. And now I would come to the scenario that I promised also in the abstract. So it is actually it's about a tool for preoperative planning of hip joint replacement, and the need for such tool comes, as you know, also from your own medical applications, from the fact that every patient has his own specific issues, and when a patient wants to choose the implant for the surgery, it depends very much on the patient which implant to use, where to place it, and things like this. So in the case he does not choose the right implant, it may lead to osteoporosis and different degenerations of bone tissue. So this is why it's important that a surgeon before a surgery gets some feedback about how the bone responds actually during the movement. So while applying some forces, which are like forces that are applied to our bones when we do everyday movements like walking or going up the stairs. So how the bone would, with the implant inserted, would respond to this. And what tells him about it is the distribution of bone stresses. So what you can actually see here, it has a graphical user interface where he can set a few parameters like add cutting planes and stuff, and he can really click, as you will see later in the video, click on the implant, like insert it and then move it around, and also these arrows which are the forces, he can adjust the magnitude of these and also the position. So in this case, what happens is that the data about this change that he applies is sent over the network to the simulation, which is running, and then the stresses are calculated, sent back to the user for the visualization. So this red, what you see, is the overview actually of the stresses. And to be able to explain the challenge here, I have to describe in a bit in more detail what is it like on the simulation side. So what happens there is first that the bone voxel information based on CT scans data is sent over the network to the simulation. So it's received on the simulation side. And then, of course, the model is generated and the problem is approximated here using finite elements. So the guys from our chair developed a variant of PFAM code. So this is what's behind. And of course, what results from this is a very well-known linear system of equations where one calculates the displacement vectors of all the vertices. So one calculates this as a result of applying different forces and also having different implant position in the bone. So what we use for solving this system is a very efficient direct solver because in this case, due to the bad condition of the matrix, iterative solvers fail. I haven't tried it myself, they told me this, and I will tell you a bit more about the solver. It is efficient, as I said, so if you compare it to Gauss or relatives, it's more efficient. So if complexity of Gauss is n cube, this is n to the power of 3/2. Nevertheless, it is if one wants to achieve higher accuracy, so do PFAM for P equals 6 or 7, it's definitely worth interrupting it. So the simulation just takes too long in this case. And then, of course, when one solves the system, you have some post-processing, and then you send back results to the user. And now let's take a look at the solver itself, which is, from our point of view, most interesting, because we have to interrupt it. So the idea of the solver is instead of having this system of equations that you usually have, like this big stiffness matrix and forces vector, and then you calculate displacements, what you do actually is you decompose your problem. So you do recursive decomposition of the domain, and in this way you, instead of this huge task that you have, you get a hierarchy of tasks. So the tasks which you store in the bottom of the hierarchy, they refer to the elements, actually, so to the smallest units. And then you have a bit bigger tasks higher in the hierarchy. Of course, always in the root you have a big system, but it's still much smaller than the initial system, you know. So what the challenge here was how to interrupt, and what we were doing is when signal occurs and we are in the middle of the processing of one node there, because we go bottom up to do the assembly, which is most time consuming actually. So in this solver, let's call it like this, we have assembly and solution coupled, kind of. So first we do assembly bottom up, and then we do solution top down. So while we're doing assembly, which is most time consuming, if something happens on the user side, this, and we're in the middle of processing one node. We're in the middle of processing one node, and then after we're finished with this node, all the other nodes which would follow, so upper in the hierarchy, are skipped. So no matter if you have a multi-threaded application, I mean in this case we were using multi-threaded simulation, all the threads, they learn that something has happened, and they interrupt their current computation so that then they start computing from the beginning. And but then, of course, if you calculate for p up to, let's say, 3 or 4, it still makes some sense. You can get the result quick enough so that this connection between your change and the actual result that you see is still somehow intuitive. So you can recognize this, which among your changes led to which result. But if you increase p to 6 or 7, I mean, everyone who is a mechanics guy says this is where it becomes actually interesting, because for p equals 1 or 2, it's nice to get some overview, but it's really not accurate enough. So for this, no matter that we interrupted the old computation, it's just, again, takes too long until you get the new result, no matter that you interrupted the old one. And this is why, again, here we were playing with different hierarchies. So the idea and the motivation is the same as for the heat conduction. We were running several instances of the simulation for different polynomial degrees. And then when the user makes a change, all of them are being interrupted. Nevertheless, you immediately get some feedback. You manage to get the feedback in between your two changes for p equals 1, for example. So you see approximately how the stresses distribution would look like. But then when you're satisfied with your current setting and you say, yeah, well, let's see what happens later, then you get it kind of refines, so you get the more accurate result. And this is exactly, I better show you this on the video instead of talking more. So this is the user interface. It was developed at the chair of Professor Westermann. They cooperate with us, so the visualization was not done by us. So you will see soon, for example, when one is moving the implant or increasing the forces magnitude, how the stresses change. And you will see first, you get some rough picture. So this is for p equals 1. For example, you see it's just, I mean, I'm not a mechanics girl, but it's not so smooth, these things. You can see how the stresses look like, and now it refines for p equals 6. You see, it looks much smoother, if one can say so. So here, for example, I believe it can even be faster if one has faster connection. The connection between our two components, so the visualization and the simulation, was not so fast. And also, here, I just, in this example, did it in a way that the updates were sent every half a second or so. So it can be even more frequent. So the update, this is completely up to the user, how frequently he wants to send the update. But it has to be still provided that he can specify this interval so that one can send it as often as one likes. So you can see, of course, with the implant, maybe it's seen a bit better. And okay, now this we increase the magnitude of the forces. And so on. So, first of all, as I already said, what is good news is we did not notice a significant overhead of the framework itself. So we were at the beginning scared that raising so much interrupts is gonna affect the execution time, but it did not more than, let's say, 2, 3 to 5%, which in this case is if one wants to play interactively, you have to pay a price at some point. I mean, and we have indeed seen that it did not affect, of course, the speed. That we had good speed up results in both case of multi-threading and distributed simulation. So these both actually refer to the temperature distribution simulation. So we tried both with multi-threading and distributed simulation. On the other hand, as I said, what happens when you increase the number of processes dramatically, I do not know. So it would be really interesting if you have a massively parallel simulation here, and you would like just to see how fast the signal can be transferred to all the processes. We can quickly try this. At the moment, of course, since, yes, I work on interactive computing and computational steering, but for this one has to get results quickly, so I usually also involve myself in the simulation part, and at the moment I'm trying several different strategies to parallelize this solver. And actually, I do not know who said that hierarchical data structures are very convenient for this, because from my experience, it's actually very tedious. It's not so straightforward. If you cut the tree, this hierarchy at some level, and then but you have I don't know 100,000 processes. What will you do with them at the top of the hierarchy? I mean, it's not very straightforward. There are solutions. I hope so. But it's just that I'm working on this now, and at the moment I'm trying some static load balancing strategy where we distribute the tasks. So we have a bunch of tasks, we estimate the complete load and then distribute them to different processes, and then I was trying different optimization strategies, how to decide which task goes to which process, but I still do not have any speed up results. There, actually, I am also scared a little bit that we will die due to the communication. It would be nice to talk to any of you who is dealing with this similar problems, or who had some experience with this, to discuss this. Of course, it's always challenging how to communicate a large amount of data, because if you imagine you have a huge result to transfer, it takes a long time if you do not do it in a good way, if you do not have opportunity to transfer the data quickly. And so, of course, this is another question for any of you who is doing this. I know that some of you are. What we were thinking of is that it would be nice if one changes something, just to transfer this part which has been changed only, but then if you receive this, you have this huge picture. You have changed it a little bit, and then when you receive this small update, this small part is being updated. You do not see much actually there. This was our thought at some point. So it would be nice when you transfer this partial result, at least to see it like maybe in higher resolution to see to be able to see this change better somehow. So these are only all the things that we were thinking of, but it's still it requires some time to work on this, and it would be again very nice to get some feedback from you. Of course, what I also said is we're always looking and grateful for new application scenarios where one can try the concept in general and see if one can interrupt via signals and apply maybe some different settings and then get quicker the result back, because all the simulations are different and there might be interesting things to learn about. I mean, if it works, it's great. If it doesn't work with your simulation, then we would like to know why. Maybe, I do not know. I know that in Ski-Run, for example, you can couple different simulations to the visualization tool, and you have several solvers at least there. Maybe one can just try with any of them to interrupt them and see if it would improve something, in the sense that one can change anything. For example, number of iterations during the runtime, because from what I saw at the moment, if you run it once and then you want to modify anything, you have to wait until the complete pipeline is executed. So maybe this is just an idea. I do not know if it makes sense. I would need to talk to some of you, and maybe then we make some conclusion together. And what I found really nice is this modularity of this concrete software. It's amazing that when you just click and you connect these modules. You take it probably for granted now, but I have experience with other codes, and actually I have realized now how important this is to be able to reuse some components and couple them easily together. So this is also something that I would like to learn about. So I would like to thank you for your attention. And some of you already know where I sit, so I will be here until the end of January. If at any point you have any idea how we can try something together, or if you would like to talk about your experience, I would be really grateful. So yes, I invite you to talk to me. Besides the coffee breaks and pizza time, yes, I would like to thank you for your attention. I'm ready for questions.
Thank you. Any questions for Jovana? Ideas? People that know something about computational? Should go talk with her.
So I have a question. When a user changes a parameter, do you recompute the entire system, or are you reusing information from the previous solution?
In which application?
Either, actually. In either of the two.
In either. Okay. So if you change something, as I said, it recomputes from the beginning.
Okay.
But we have different hierarchies, and this then lets us see some overview, get some feedback at least. And this happens instantly, but then you get, of course, higher accuracy results when you wait, when you stop interacting. But it starts from scratch, except that in the heat conduction example, we are reusing the results on the coarser grid as an initial guess for the results on finer grid. Yeah.
How easy is it right now for people to be able to plug in different kinds of computationals or different problems?
How easy is this?
What do you have to do right now?
For the framework,
Yeah.
you mean? I mean, we say framework. Actually, I hate this word because what is a framework? It really depends on the... but to be honest, I got this bone code. It's a good code in some sense. So, for example, error handling is great. So this is what my teaching assistants were always saying. This distinguishes good programmer from bad programmer. But it's old code, and it took 10 or 15 years to develop this whole functionality. They did not have clever approach like you, in the sense that they had modules. You have files sometimes with, I don't know, 100 if-else clauses, which is really horrible. But what I realized is that with this concept, you do not have to interfere with the whole code. So most of the things that you change are actually in the signal handler, which is something that you add. And you initiate this signal raising, but this is few lines of code, basically. And for me, the most of the effort was changing the communication pattern sometimes, because sometimes we had blocking, very rigid communication pattern, and I realized with this I cannot profit from interrupts at all. I have to have asynchronous communication there. But this is not part of the framework. This is just, for me, it was, you want, if you show some results, you cannot discuss if this was your part of the job or not. It's all about the results that you get, and for this I had to change this. But for the insertion of the signals and stuff, it's really minor changes. But one has, of course, to discuss with the simulation guy or girl if modifying something can be dangerous. So sometimes it's not just nice to change any random parameter. It does not make sense sometimes from physical point of view, and I don't know this. So this is something which one has to learn from the simulation person, to see how to skip the rest. What is the most time-consuming part of is it a solver, is it something else? So this is, from this point of view, one cannot make a framework which is generic enough. But we like so far the concept, at least this idea that, and we try to gain experience. Maybe at some point we have something which is really applicable to different. Yes.
So once you've sent the signals to all the various processes, is there something that waits to make sure all the processes have shut down before it starts the new simulation? Like I could see maybe getting out of sync where some processes are still, I guess it's only in a millisecond.
Well, if you have...
If you could respond quick enough and start the next one, would be accidentally getting information from...
You mean in parallel distributed simulation, for example? Well, of course, you have to synchronize at some point. You have to synchronize at the point where you have to send the result, because you have to have the overall result. But what happens in the meantime, it's you do not have to synchronize them for everything which happens in the meantime. So they can do their work. If they're interrupted, they start over again, each of them. And as I said, it must be that if you have 100,000 processes, you have bottlenecks, you have different bottlenecks. You have bottlenecks when sending back the result, you have bottlenecks when sending the signal towards the simulation processes. This is not something which one would have to try, really. We haven't tried it. But on up to 100 processes, we have realized at least that probably due to this very short interval in which the interrupts are raised, they're pretty well synchronized. Because we invoke signals every millisecond, so...
So as long as it doesn't take much more than a millisecond for the signals to get propagated?
Yeah, well, as I said, it's if you have 100 processes and you have this hierarchy, communication hierarchy, well, it's not actually that much that it takes to reach all of them, like something is sent. Because the data which you send from the data which is sent by the user is usually not a big data. I mean, the update data is not as large as simulation results usually. So, yeah, this is what we have experienced so far. Yes?
So I have a question, how you handle the inconsistency between different levels? Because sometimes when you go to lower level, then actually the results look completely different. So
Okay.
how can you handle that?
Well, first of all, with signals, as I said, it's really dangerous. I mean, you have to take care, first of all, that the data that you modify in the signal handler is consistent. You have to take care that you have to take care about atomicity of your operation. So you must, sometimes you're not allowed to interrupt some operation in your simulation. So you have to take care that some, well, now I can talk to you later about the details, just demonstrate you what may happen. But what also may happen is that you may allocate some memory, then you're interrupted, you want to skip the rest. So you have to take care that the memory which is allocated previously is released before you start the new computation. So these are all the things we for these particular scenarios we have taken care of. But I do not know what other scenario one can get, and then one would have to sit and see what is special about this simulation and what one has to do to prevent inconsistency.
So no, this one actually, this question is about the inconsistency in a numerical simulation.
Okay.
Well, you have different level of weight, and when you run on the different level, actually, it gives you different result due to the width side of because there's some interpolation or something like that. And when you run the simulation, it gives you different result. So that you say when I change one parameter, in the low level, this behavior that I saw. However, when you go to the final level, actually the behavior is completely different.
Okay.
So the question is how you handle some kind of numerical inconsistency. Just one way is that actually I think it's better to go in the reverse direction. That means somehow you use the result from final weight, and to interpolate on the lower weight as a starting point. That's one. So that it's consistent between the final weight. That's what we want to see, and the lower weight. That's what we want to run in fast, and then you do some simulation on the lower weight. Wait fast to give some immediate feedback, and then when people stop interrupt, you can run a final weight. That's one way. I'm not sure if it's the best way or not.
No, I'm just thinking, I mean, when you change something, then you do not have a result on the final grid. So this is
you can use the previous result from the.
But is this something which you can use really? I mean, if you make major change, I don't know. I mean, I'm wondering what can you do then?
Probably he meant like the first example when you did the red and this. So maybe he meant that from the fine grid you take the initial guess and sort of resolve it on the coarse grid for the next value, something like that.
Yeah. To restart for the.
But I'm not sure if I get how can you, I mean, you change something and then you do not have results yet on the fine grid. So how can you, what do you use for initial guess then?
Well, if you change something, you don't have a result on the coarse grid either.
Yes, you do.
So you just have the.
You have complete result on the coarse grid. It's just that, as I said, I do not know, it's probably even in this temperature distribution that a small error is introduced due to the fact that we were using this result on the coarser grid and kind of extrapolating it on a finer grid as an initial guess. So it might be, I mean, when you look at the visualization scenario, it was just for trying out the concept. We were not dealing with the error there, really. But I do not see still, if one would like to improve this or change this, how can you take the result on the finer grid if you do not have it? I mean, exactly the point is that you do not have this result, and this is why you have only the result on the coarser grid, and then you have to wait until you get the result on the finer grid. But I mean, maybe we can afterwards sit and really, like, you know, draw the picture and discuss it in more.
There's another question. Is what happens if people want to change several parameters at the same time, or maybe one parameter should be changed when the other is changed. So what happens?
Well, to be
do you have any idea how to handle it?
What's actually in current implementation? So whenever you change something, it is the simulation is interrupted for each change.
But right now you can allow only one parameter change or multiple parameter change at the same time.
When you say parameter, for example, I mean you have these user interfaces. So if you're moving a pillar around, all of this change in the position are separate changes, and of course it depends on the frequency of sending the update. When are these things gonna be reported to the simulation? So if you specify, I'm gonna send the update every 10th of a second, then all these things will be reported. So the last setting after 10th of the second will be sent to the simulation. If you do it every millisecond, then you know what I mean. So you have to interrupt every time you make a change. If you want all the data to be transferred there, then it becomes aware that something happened every time you make something. Of course, what you can do if you like is in timely fashion check for this. So you can set your check interval to be longer, and then you do not receive everything separately. If your alarm rings every hour, then until next hour you will not know what happened.
Within SkiRun, we have dependency graphs, and so if you change something, it follows up the tree to figure out what else has to change if that changes. You probably have something similar with that. So you can make sure that you just can't change something in isolation that depends on something else. You have to make sure that whatever is dependent on that change is executed. So you just have to follow the graph up as far as you need to go.
Yeah, I think that's one way. And the other thing might relate to some kind of user design. I mean, sometimes you must allow to change control. You have two rows and you want to move. It's in parallel, something like that.
Yeah.
So you should allow to select two rows at the same time and then move at the same time or something like that.
Sure.
So that means somehow you change two parameters, but using the user interface. That's one way. Another way that, as you say, that's one way. You have to make sure that you have some quality on the parameter. I mean, somehow it cannot go out of wow or something like that.
Right. Yeah, you have to try to help the user do things that aren't stupid, but it's still, you have to have a user that's informed enough that understands what's going on. So.
Yeah, of course. I mean, user. It's up to user also to give certain intelligence you know, because we cannot know what kind of simulation we have and what kind of, how to interpret all the results. So if user says, I want to send some part of the data all together, then he has to let us know, I want it this way. How can we know this? It's just, unfortunately, we said at the beginning we want a generic framework, and I mean, it sounds great, but there are all sorts of requirements, so.
Okay, thanks very much.